Boltzmann's entropy formula is probably one of the most difficult equations in all of physics. Not because the equation itself is that confusing, it isn't. It's just two variables, one constant, and a trig function. But because it relates two things, entropy and the probability of being in different energy states, they're both really difficult to understand. So as I usually do, I looked into the history of this equation. Who made it and why was it made? And I found it was created by a scientist named Max Planck in 1900 and written almost identically to the modern form in 1901. But wait! Why is it called Boltzmann's equation? And why is the constant in it called Boltzmann's constant? And why is it even on Boltzmann's gravestone if Planck created it? Good questions. Ready for the answer? Let's go.
Electricity, 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 electricity.
I would like to start with the origin of the idea of entropy. In 1854, a German scientist named Rudolf Clausius noted that absorbing less heat at lower temperature was equivalent to absorbing more heat at higher temperature. Therefore, he called the heat over the temperature the equivalence value, and he would later call the equivalence value the entropy. By 1862, Clausius found that any decrease of equivalence value on one object would require an increase of equivalence value, or entropy, on the other objects, so that the total equivalence value for any process for a closed system had to be greater than or equal to 0. By 1865, Clausius renamed the equivalence value the entropy and gave it the letter S, and defined the second law of thermodynamics to be the entropy of the universe can only increase, which is a modern definition. Now I want to take a moment to talk a little bit about the history of probability in thermodynamics. And for that, I'm going to start with, ready for it? A German man named Rudolf Clausius. In 1857, 3 years after Clausius's first paper introducing the equivalence value, Clausius wrote a paper on what the temperature meant about the motion of molecules. In this paper, Clausius became the first person to introduce rotational and vibrational motion of molecules, as well as linear motion. Even with these limitations, Clausius found that molecules move at incredibly fast speeds. For example, hydrogen gas at 0 degrees Celsius should move at slightly more than 5 times the speed of sound. After reading Clausius's paper, another scientist published an objection. If molecules are moving that fast, how come cigar smoke doesn't just fill the room faster than the speed of sound? Clausius thought it was a very interesting objection, but instead of invalidating his theories, Clausius thought it would all work out if the gas molecules are moving very fast, but not very far. In other words, in a cigar smoke or in any other gas, there are a ridiculous number of molecules moving in all directions, but they don't get very far before bouncing off another molecule and changing direction. So that even though the individual gas molecules are moving very quickly, the gas itself diffuses slowly. Clausius then came up with a term that he called the mean length of path, which was, quote, how far on average can the molecule move before its center of gravity comes into the sphere of action of another molecule. Conveniently, an English scientist named Frederick Guthrie was a fan of Clausius and was also bilingual, and Guthrie translated Clausius's work into English and published it in February of 1859. 3 months later, a 27-year-old Scottish scientist named James Clerk Maxwell wrote a friend that Clausius's paper had inspired him to determine the mean path by, quote, comparing it with phenomena that seemed to depend on this mean path. Between 1860 and 1866, Maxwell published a series of articles on what he called the dynamical theory of gases, although he admitted it was Professor Clausius to whom we owe the most extensive developments of the dynamical theory of gases. During this same time, the busy Maxwell also published a couple of papers on electricity and magnetism, the results of which are known as Maxwell's equations. Funny story, in 1861, Maxwell was once stuck in a crowd of people, and Michael Faraday, referring to his work in statistics, yelled out, "Ho, Maxwell, cannot you get out?" If any man can find his way through a crowd, it should be you. Anyway, Clausius had some minor complaints about Maxwell's theory, but there was another German scientist who was entranced, and his name is Ludwig Boltzmann. Yes, he is involved. Boltzmann was 13 years younger than Maxwell and went to college in 1863. While still an undergraduate, one of his professors immediately appreciated Boltzmann's brilliance, and according to Boltzmann, he decided, quote, to hand me a copy of Maxwell's papers on gases. However, at the time, I didn't understand a word of English, so he also gave me an English grammar book. Boltzmann managed to translate Maxwell, and he soon was publishing his own papers on the theory of gases, and 3 years later, he earned his PhD on the dynamical theory of gases, and by the time he was 25, he was made a full professor. Aside from his eerie intelligence, Boltzmann was also known for his great teaching prowess. Lisa Meitner described him as the best teacher she ever had. His humor, like when he said he was tolerably good at mathematics, except, quote, when I'm counting beer glasses, and his oddly naive view of reality, like when he consulted a professor of zoology to determine how to milk a cow. Maxwell and Boltzmann's work on statistics and thermodynamics led to the Maxwell-Boltzmann distribution, or equations for the probability of different speeds of gases, that is still used today. Maxwell started off being confused about entropy, but once his confusion was cleared up by an American named Josiah Gibbs, he decided to use his methods of studying statistics in molecules on entropy. This led Maxwell to decide that the truth of the second law is therefore a statistical, not a mathematical truth, for it depends on the fact that the bodies we deal with consist of millions of molecules, and we can never get hold of single molecules. Or as Maxwell amusingly put it to a friend, the second law of thermodynamics has the same degree of truth as the statement that if you throw a cup of water into the sea, you cannot get the same cup of water out again. Not surprisingly, Clausius was not pleased with Maxwell for downgrading his law like that. However, he had bigger issues. First, in 1870, Clausius was injured in the Franco-Prussian War when he organized an ambulance corps. Second, in 1875, Clausius's wife died in childbirth, and Clausius took time off his research to focus on raising his 6 children and teaching. Clausius always taught, even on his deathbed. Young Boltzmann, however, was motivated once again by Maxwell, and now dived into the relationship between statistics and entropy. In 1872, Boltzmann wrote that the molecules of a body are indeed so numerous and their motion is so rapid that we can perceive nothing more than the average values. Hence, the problems of mechanical theory of heat are also problems of probability theory. By 1877, Boltzmann started to work on the relationship between probability and entropy. He started with the idea that, quote, in the game of lotto, any individual set of 5 numbers is just as improbable as the set 1, 2, 3, 4, 5. It's only because there are many more uniform distributions than non-uniform ones that the distribution of states will become uniform in the course of time. Boltzmann even declared that one could even calculate from the relative numbers of the different state distributions their probabilities. So in October of 1877, Boltzmann set out to find equations to figure out how many distributions there could be. Boltzmann ended up writing over 50 pages of dense, equation-rich material, still not translated out of German, where he broke up the energy of molecules into different sections and predicted the probability of ending up with different scenarios. He wrote, applying this to the second law, we can identify the quantity, which is usually called the entropy, with the probability of the condition in question. However, Boltzmann didn't make an equation that related the entropy to this newly defined probability. Fascinatingly, both Maxwell and Boltzmann could have had the help of their scientifically minded wives. Catherine Maxwell had no scientific or mathematical training, but it was recorded that she helped her husband with his experiments. In fact, in 1877, a friend wrote Maxwell asking for data on viscosity, and Maxwell wrote back, "My better half, who did all the real work of kinetic theory, is at present engaged in other researches. When she is done, I will let you know the answer to your inquiry." Boltzmann's wife, Henriette Boltzmann, actually tried to study physics and mathematics at school, and she even basically sued to be able to audit classes on Boltzmann's suggestion. In his marriage proposal, Boltzmann referred to her as a mathematician and said, "It seems to me that permanent love cannot exist if a wife has no understanding and enthusiasm for her husband's efforts, and is just his maid and not the companion who struggles alongside him." However, she was probably pretty busy raising their 5 children and dealing with his depressed moods. The Maxwells and the Boltzmanns worked together for several years, but then James Clerk Maxwell fell ill in the spring of 1877, and he died of stomach cancer when he was only 48 years old in November of 1879. Henriette and Ludwig Boltzmann continued to publish work on their theories of statistics and heat and probability and entropy. However, they felt increasingly outnumbered in Germany, as the existence of molecules was considered an avant-garde idea that was deeply unpopular among the scientific establishment. Now we finally get to Max Planck. Planck was 14 years younger than Boltzmann, and in 1877, the same year Maxwell fell ill and Boltzmann wrote his very long paper on probability, Planck went to graduate school and found to his disappointment that the great researchers there were pretty awful teachers. He decided he was better off just reading original papers. Years later, he recalled, quote, "One day I happened to come across the treatises of Rudolf Clausius, whose lucid style and enlightening clarity of reasoning made an enormous impression on me, and I became deeply absorbed in his articles with an ever-increasing enthusiasm. I appreciated especially his exact formulation of the 2 laws of thermodynamics." By 1879, Planck got his PhD in the second law of thermodynamics. However, the effect of my dissertation on the physicists of those days was nil. None of my professors at the university had any understanding for its contents. I found no interest, let alone approval, even among the very physicists who were closely connected with the topic. Even Clausius was indifferent, and Planck went all the way over to his house, but with no reply. Despite that, Planck managed to become a professor in Berlin in 1889. Planck then got into a debate with people called energetics, who believed in energy but not entropy, and also did not believe in molecules or believed in the absolute zero scale for temperature. In this debate, Planck found a strange defender, Ludwig Boltzmann. In 1896, Boltzmann had a public debate with an energetic on the issue, which seemed to convince at least the younger generation of the validity of the second law. But Planck also felt that Boltzmann was attacking him. See, Planck never liked Boltzmann's theory of statistics, saying, "I regarded the principle of the increase of entropy as no less immutably valid than the principle of conservation of energy itself," whereas Boltzmann treated the former merely as a law of probabilities. And for that reason, I was not only indifferent, but to a certain extent even hostile to the atomic theory, which was the foundation of his entire research. Meanwhile, Planck had moved on to a new subject that would eventually force him to accept Boltzmann's theory about probability. See, in 1894, an acquaintance of Planck's named Wilhelm Wien had made an equation to describe the distribution of radiation from a perfectly absorptive object called a black body that was based on experimental data but had very little theoretical background. Planck thought he had a unique approach to the theory because he was worried about entropy and no one else was. Years later, he recalled, "It was an odd jest of fate. The lack of interest of my colleagues in entropy now turned out to be an outright boon." By 1899, Planck published his results, and for a short while, it was called the Planck-Wien law. However, there was a problem with the law. It didn't work at low energies, and in October of 1900, Planck was told by an experimentalist that he needed to tweak his equation. Without any time to prove anything, Planck made up a new equation that would work both at low frequencies and also would look like the Wien law at higher frequencies. The experimentalists were delighted, but Planck was distraught. A theoretician is not supposed to just guess an equation from the experimental data. They're supposed to derive it from fundamental ideas. He recalled, "For 6 years I had struggled with the black body theory. I knew the problem was fundamental and I knew the answer. I had to find a theoretical explanation at any cost, except the inviolability of the 2 laws of thermodynamics." So in a self-described act of desperation, he turned to Boltzmann's method of statistics with entropy. After a few weeks of intense work, Planck decided that, quote, "Since the entropy S is an additive magnitude, but the probability W is a multiplicative one, I simply postulated that S equals K log W, where K is a universal constant." A quick note about the log function. It is the inverse of the exponent function. So if they multiply the input by 10, the value of the log base 10 increases by 1. That's what Planck meant about additive and multiplicative. Here is the famous equation, but what does it mean? First, it means that entropy has an absolute value that one can calculate from the properties of the molecules in the material. Although not as easy to measure as temperature, say, entropy has a definite value for any object with any arrangement of molecules. The more complicated the arrangements are, the more entropy the object has. Secondly, the constant K has a value above and beyond just a relationship between probability and entropy. K is used in many different equations, including the heat capacity and the relationship between kinetic energy of particles and the temperature. With an accurate measure of K, one could predict many microscopic things that weren't known accurately at the time, like the mass of a hydrogen atom and even the charge of an electron. In fact, as of 2019, K is only one of 7 basic constants, like the speed of light, that all of our units of everything is currently based on. But then Planck had a problem. If the energy was continuous, then it could be split up into infinitely many arrangements. So therefore, the probability would be infinite and the entropy would also be infinite. As Planck put it, if the energy is, quote, "considered to be continuously divisible quantity, this distribution is possible in infinitely many ways." For that reason, Planck constrained the energy to be created in little energy packets, with energy equal to a constant h times the frequency. This is the origin of quantum mechanics, so you could argue that Boltzmann's entropy equation started the quantum revolution. In addition, h is another one of the 7 fundamental constants that we base our units on. Then, with the voluminous data he had on blackbody radiation, Planck managed to get values for his 2 constants, h and k. Startlingly, h is around 1% of its current value, and k was about 2.5% off of its current value. Even more impressively, with his value for k, Planck managed to get a value for the charge in an electron within 2% of its current value, when the other 2 accepted values at the time were 73% too low and 35% too high. Now you might ask how this equation and the constant got named after Boltzmann and got put on Boltzmann's grave. Well, Planck had a lot to do with this. See, when Planck first introduced the entropy equation, he was using a new method for him, and therefore said he was, quote, "introducing probability considerations, the importance of which for the second law of thermodynamics was first of all discovered by Mr. Boltzmann," which implied to people who hadn't pored through Boltzmann's 50-page long paper about probability that Boltzmann had originated the equation. Then, in September of 1906, Boltzmann's depression got the better of him and he committed suicide. At the same time, Planck was giving a series of lectures on heat radiation and learned through some of the scientific memorials of Boltzmann that 4 years before Planck had written his equation, Boltzmann had written that a function that was related to the entropy was also related to the log of probability. I know it's a little confusing. Anyway, for that reason, during these lectures, Planck said that, quote, "the logarithmic connection between the entropy and probability was first stated by Boltzmann in 1896. And then he added that it didn't really count because Boltzmann never had a constant, and as Boltzmann never directly linked entropy to the log of probability, Boltzmann had created an unspecified value for the entropy. Planck added that the absolute value for the entropy is a step of fundamental importance as it leads necessarily to the hypothesis of quanta. A few years later, Planck published these talks as a book, which had the opposite of the desired effect, as that one quote is still to this very day used to justify the naming of the equation that Planck created to Boltzmann. Also, during the 1910s, it became very popular to name constants after the scientists who discovered them. For example, in 1913, Niels Bohr wrote a paper about the arrangement of atoms, where he named the constant h in E = hf, Planck's constant. Bohr's paper was a hit. Years later, Einstein recalled that Bohr's paper, quote, appeared to me like a miracle, and appears to me as a miracle even today. This is the highest form of musicality in the sphere of thought. 6 months after Bohr's paper, English scientists Esser and Ernest Griffiths wrote a paper on the specific heat of metals at very low temperature. And as far as I can tell, they became the first people to call K Boltzmann's constant. This paper was not revolutionary like Bohr's, but it did include a lot of very interesting data, and it also included an overview of quantum mechanical view of solids, so it was widely read. Pretty soon, most scientists were talking about quantum mechanics, and they were using Planck's constant and Boltzmann's constant to do so. By 1920, when Max Planck won his Nobel Prize, he complained that K was, quote, often referred to as Boltzmann constant, which he found to be a peculiar state of affairs, as, quote, to my knowledge, Boltzmann himself never introduced it. By the 1930s, it became trendy to name the equations after their inventors, and soon S = K log W was referred to as Boltzmann entropy equation because K was known as Boltzmann's constant. At around the same time, the aldermen of Vienna realized that Boltzmann's grave was kind of decrepit. The aldermen decided that, quote, the city of Vienna and its people are proud of the man of genius who lived here, and they have endeavored to find a burial place worthy of him. For that reason, they moved Boltzmann's body to a place of honor near Brahms and Beethoven, and they created a marble bust of Boltzmann. And a local scientist named Hans Thüring had them add what he called Boltzmann's greatest scientific achievement to his grave, i.e. S = K log W. So that's how Boltzmann's equation ended up on Boltzmann's grave, even though Boltzmann's entropy equation should probably be called Planck's entropy equation, and Boltzmann's constant should definitely be called Planck's constant, except we already have a Planck's constant, so that's super confusing, so I guess we aren't going to fix it. So now I'm at a bit of an impasse of what I should do for my next video. So I'm going to do something I've never done before. I'm going to let you guys vote on what you would like to see for the next video. Should I make a video about the tragic and sometimes heroic life of Max Planck? Or should I make a video about Niels Bohr's musical quantum model of nature that we still study even though we know it's wrong? Or should I go back in time and talk about an amazing woman I miss? A scientist in the 1700s who brought electricity to Italy, whose marriage was considered a travesty against science? Or should I skip all the theory and jump into the wild story of the teenager who invented television? Comment in the bottom and let me know. Or if you want more of a vote, you can become one of my patrons. Thank you, patrons. And then for just $1 a video or $5 a video, you get thanked, you get the videos early, and your vote gets more of an influence. There's a link down below. Remember, the options are Max Planck's life, Niels Bohr's model, Laura Bassi's influence, or Farnsworth's TV. I do want to hear from you. Also, if you have any questions or went too fast or too slow or move my arms too much, please tell me in the comments. I can't stop moving my arms. That's part of it. Thank you so much for watching. Remember, subscribe, hit the silly bell thing. I don't make that many videos, so it won't bother you. Share it on social media. Give me thumbs up, all that jazz. Okay, have a nice day. Thank you. Greater value of the increase. I'm gonna get this. I'm gonna get it. I believe in myself. Gotcha.